So, hello everyone. Welcome to week 7 of the NPTEL course on Foundations of Cryptography. So, I will, as usual, first discuss the assignment questions of week 6, and then I will proceed to discussing some questions on week 7 topics. Okay. So, let me first share my screen. I am audible, right?
Yes, ma'am.
Okay, thank you. Is my screen visible?
Yes, ma'am.
Okay. So let us begin with week 6 assignments. So first question was this: which of the following options is or are correct? Davis-Meyer hash construction is unconditionally secure since block ciphers are secure. So let us proceed one after another. It would be good if you could also response. Okay. So about the first statement, Davis-Meyer hash construction is unconditionally secure since block ciphers are secure. Is it true? So does Davis-Meyer hash construction security is completely dependent upon only block cipher security or not? Okay. So basically it is not, the statement is false because if you remember, so in Davis-Meyer hash construction, we basically get a collision resistant fixed length compression function which is basically secure due to the fact that we assume ideal cipher model. Okay, so in ideal cipher model, basically you assume that the output of block cipher is kind of random, right? And you do not know the algorithm of the block cipher. So you get the block cipher as a oracle service, both the forward direction and the inverse direction. So the block cipher and its inverse both are provided as oracle service, and in such ideal cipher model only you assume the Davis-Meyer construction to be secure. So only secure block cipher is not that is required. Apart from that, we also assume block cipher to be providing oracle service. Then only in the ideal cipher model we get the Davis-Meyer hash construction to be secure. So next statement says that construction of Markle-Damgard transformation will always add a padding to the message which depends upon the length of the message. This is also true. So this is purely from the construction point of view, how you get a fixed length collision resistant compression function and then transform it to get a hash function that can hash any length of message to fixed length of message. So there we have seen that how padding is done in the lecture. Next statement says output of a block in the Davis-Meyer construction is given by fmt XORed with t, where m is a block of message and t is the IV or output of the previous block. So is this true? Anyone? This is exactly how the Davis-Meyer construction is given, right? So you have this initialization vector for the first block cipher evaluation. So m is the message block which is acting as a key to the block cipher, and t is either the initialization vector for the first evaluation, and then onwards t is the output of previous block. So you have a block of messages given, right? And in this way you basically evaluate the so you can get a compression function in this manner, and then further apply Markov-Damgard transformation to get a arbitrary length hash. Okay, this statement is true. Collision resistance of the Markov-Damgard transformation is independent of the collision resistance of the compression function used in its construction. Is this statement correct? Anyone? Okay, so this statement is not correct. Why? Because as I already mentioned, that the building block of Markov-Damgard transformation is the underlying compression function, which is collision resistant as well. So collision resistance of the underlying compression function also gets retained in the way Markov-Damgard transformation works, so that the final hash function for arbitrary length messages that we get also has the same collision resistance property. So in the proof also, if you remember the proof of collision resistance of the arbitrary length hash function that was constructed using Markov-Damgard transformation, there we, in the proof we had seen that if there is a collision in that arbitrary length hash function obtained from the Markov-Damgard transformation, then that would imply a collision in the underlying compression function. So of course the collision resistance of the underlying compression function is related to the collision resistance of the final arbitrary length hash function obtained from the Markov-Damgard transformation. So the collision resistance of both the cases are related to each other, and collision of the Markov-Damgard construction implies collision in the underlying compression function. So they are not independent of each other. So the fourth statement is not correct. Coming to the second question, given h and g are collision resistant hash functions, which of the following is or are collision resistant? So I think this kind of questions are already discussed in the week 6 topics. So anyone would like to answer? First function is given as f1x equal to h of x concatenated with a single bit 1. Given h of x is a collision resistant hash function, is f1x also collision resistant? Acha, Kaushik Das is saying all. All are collision resistance. Yes, you are correct. By the way, I will request you that if you are answering, then please unmute yourself and say it in the meeting itself. Otherwise, if you write in chat, so it is bit difficult in Google Meet to go back to the chat screen. Like in Zoom, I could see the chat from the screen itself, but I have to go back to the Google Meet tab to see the message. So better you just unmute yourself and say. But anyway, Kaushik, your answer is correct. All of them are collision resistant hash function. Maybe I should just get a quick explanation that let's say f1x is not collision resistant. Okay, then what happens? is not CR, I am writing assume. So if this is the case, then it is easy to find out two input x1 x2, okay, such that f1 of x1 is equal to f1 of x2, and that would imply h of x1 concatenated with 1 is equal to h of x2 concatenated with 1. This is how the function f1 is defined, and that would imply, if we just ignore the last one bit, then we see that rest of the output bits, so we get this, right? H of x1 is equal to h of x2, and that implies a collision, right? So if I get x1 x2 colliding pair for function f1, then I can return the same x1 x2 as colliding pair for the hash function h, but we already know that h is collision resistant, so it is easy to see that by contradiction we can say that f1 is also collision resistant. And similarly the other one also, you can easily say that if such x1 x2 exist for f2 as well, that would imply h of x1 concatenated with g of x1 is equal to h of x2 concatenated with g of x2, and that individually would imply that h is also not collision resistant and g is also not collision resistant, because it is easy to return x1 x2 as colliding pair for both h and g. So f2 is also collision resistant, and same argument works for f3 as well. So all of the above is the correct answer. All of them are collision resistant. Okay, choose the correct options from the following. Ideally, same hash function can either be used as a compression or an expansion function. Is it correct? Can hash function be used both as compression and expansion function? So compression means where the output length is lesser than the input length, right? Essentially it has to be. When we say that a function is a compression function, that means that if the function is, let's say, from m bit to n bit, then n has to be less than m if f is compression function, right? Whereas if g is another function, say u to v, then v has to be greater than u if g is expansion function, right? So now the question is, can same hash function be used as compression or an expansion function? Okay, what do we how do we define hash function? We write this, right, that any binary string or binary string of arbitrary length should map to a fixed length string, right, for a hash function h. That is how we write. And there is some other cryptographic property to satisfy, like collision resistance, pre-image resistance, etc., second pre-image resistance. Anyway, so for hash function, so since we are writing the star here, so any length, so it can be the case that we get the L bit length output from some L1 bit length input where L is greater than L1, or it can also be the case that we get a L2 bit length input string, and then by applying hash function h we get L bit length output such that L is less than L2. So both as compression and expansion function, a hash function can behave. Okay, a single hash function can behave as both compression function and expansion function for various lengths of input. Okay. Second statement says, so first statement is correct, right? This is correct. Second statement says that cryptographic hash functions are used in data compression, deduplication, virus fingerprinting, etc. So this is correct. Anyone? You can just unmute yourself and say, so this statement is correct or not? Hash function is used in data compression, deduplication, virus fingerprinting. What about data compression? So you have a variable length of data, you can get a digest of that data by compressing it, right? In a way that, let's say you have two files of different lengths, but hash of those files have the same length. Okay, so, and also the collision resistance property is necessary here, because two files cannot or should not have same hash value or digest value. So yes, cryptographic hash function can be used in data compression, this is true. Deduplication also is something. So let's say in the cloud, user 1 also uploads the same file and user 2 also uploads the same file independently, but cloud finds out that both of the user are trying to necessarily upload the same file. So what cloud can do itself is that it can just keep only one copy of that file and give the pointers to it to two different user, right? So that it does not have to store the same file again and again, and that will be a wastage of storage, right? So that is deduplication, and there of course, as I said, that pointer to same file, or that would mean also that hash of same file are given to different users. So that is where deduplication comes to play, and cryptographic hash function can be used to achieve that. And virus fingerprinting also similar thing, that whenever we are downloading something and if our software finds out that the hash of that downloadable file matches with some already blacklisted hash function for some malicious executable file or something, so then it can raise a warning or something. So that is virus fingerprinting. So for a malicious code, you can have its corresponding fingerprinting by using the hash of that particular file. So yes, cryptographic hash function can be used in data compression, deduplication and virus fingerprinting. So this statement is also correct. The possibility of collision is always present in a hash function. Is this true? We are always talking about collision resistant hash function. So does that mean that there is no collision at all? So there cannot be found any two such input x1, x2 such that h of x1 equal to h of x2 never occurs. Is this the case? Anyone? Possibility of collision is always present in a hash function. This is a true statement or false? True, right? Right. So because there is always this possibility of collision, the main reason being that you are basically going from arbitrary length string to a fixed length string, right? So you have a limited range value, right? So let's say if you are allowing L bits in your output of hash function, that means you have 2 to the power L different outputs available for various values of input. So whenever you are querying the hash function for at least 2 to the power L plus 1 number of different inputs or distinct inputs, then you will certainly find two such inputs here such that they both map to the same output here due to pigeonhole principle. Okay, because at the worst case it can be the case with 2 to the power L different input queries, you get 2 to the power L different output values of the hash function. But whenever you are querying 2 to the power L plus one single or one extra input, there has to be a collision. So collision is always there, but what we try to ensure in cryptographic hash function with its collision resistant property is that to find that collision is hard, or for a probabilistic polynomial time adversary there is a negligible probability to find such colliding pairs of input. So collision probability is always there, but it is finding that collision is always negligible. The identity function is not collision resistant. Is it true? So what is identity function? Identity function is this: f of x equal to x. Output is same as the input. So is this function collision resistant or not? Anyone? Is identity function collision resistant or not? This is the function f of x equal to x. Can you find two such x1 and x2 such that x1 is not equal to x2 but f of x1 is equal to f of x2? Is it possible for identity function? Very simple, trivial question. I would like to hear the answer from you. F of x equal to x, is it a collision resistant function or not? Anyone? So if I say it is not collision resistant, do you agree? I am saying that f of x is not collision resistant. Is it true? So let's say it is not collision resistant. That would imply that there exists such x1 and x2 for which f of x1 is f of x2. Also x1 should be not equal to x2. Now the way identity function is defined is that f of x1 is equal to x1 only and f of x2 is equal to x2 only. So it is implying that x1 has to be equal to x2, although we initially assumed due to the non-collision resistant property of the function f, we assumed x1 is not equal to x2. However, the fact that f of x1 equal to f of x2 will imply x1 is equal to x2. This is a contradiction. So we say that f of x is indeed collision resistant, because always for each input you get itself in the output. So you cannot find two such different inputs for which outputs will be different, because then outputs will you will not find two different x1 x2 such that their function output will be same. You cannot find that because the output is nothing but the same as input only. So if inputs are different, outputs are bound to be different. So f of x is collision resistant. This is very simple, right? So okay. Which of the following statements are incorrect? So first statement says that information theoretic maps are secured against an adversary running for exponential time. Information theoretic map. So anyone? They are like objective type of questions, right? What is the definition of information theoretic map? if you remember, in information theoretic security, we always assume an unbounded adversary but allow a negligible probability of winning. So it is true that information theoretic MACs are secure against adversary running for exponential time, because unbounded adversary means that we allow the adversary to run for any amount of time or exponential amount of time. However, still, although we are allowing the adversary to have unbounded computational power, we still are able to prevent the forgery of MAC, or prevent the fact that an adversary will be able to come up with such message comma tag pair such that tag is a valid tag for that corresponding message. That probability will be upper bounded by a negligible function. So first statement is correct. Perfect unforgeability is exactly analogous to perfect secrecy. Exactly analogous. It is true. Anyone? So in unforgeability game, we say that the probability that an adversary comes up with a valued message tag pair, that probability is negligible. However, in perfect secrecy, we say that the adversary manages to distinguish between encryption of two different plain text, right? So that probability is exactly 0. Okay, with 0 probability it is able to distinguish. So it is not exactly analogous. Okay, one-time IT secure MAC is exactly analogous to one-time pad used in encryption. So IT secure MAC, already I said that information theoretic security allows the adversary to have unbounded computational power but allows the adversary to win with a negligible probability, whereas in case of perfect secrecy, or in case of one-time pad, which is a perfectly secure encryption scheme, there the adversary is still unbounded, or it has unbounded computational power, but what we say is that its distinguishing advantage in distinguishing between encryption of either M0 or M1, that is exactly 0. Not even negligible probability is allowed in case of perfect secrecy. Okay, our construction of MAC is to first create a fixed length digest from an arbitrary length message upon which a MAC is computed. Is this true? Given an arbitrary length message, it is saying that you first create a fixed length digest from that and then apply the MAC algorithm on that fixed length digest of your arbitrary length message. That is how MAC is computed for arbitrary length message, it is saying. Is this true? Okay, so this is also true actually. If you remember, there is this hash and MAC paradigm where we say that given arbitrary length message, first hash it to a fixed length digest and then apply the MAC algorithm on that digest to get the tag of that message. So that is how the hash and MAC paradigm works. So fourth statement is correct actually. This one I think we discussed last week also. Quickly, anyone would like to answer? I will go through the question once again. So it's given that let pi 1 and pi 2 be two MAC systems. Pi 1 has corresponding tag generation and tag verification algorithm denoted with tag gen 1 and tag verify 1, and pi 2 also has its own tag generation and tag verification algorithm denoted with tag gen 2 and tag verify 2. both of the MAC scheme are defined over key space of n bit length binary string, and both the key generation algorithm for pi1 and pi2 output a random key from the key space. It is given that either pi1 or pi2 is a secure MAC, but you don't know which one. Then which of the following statements are correct? First statement says that if you define another MAC scheme pi with its corresponding tag gen and tag verification algorithm over key space of 2n length binary string, and you define the tag generation algorithm like this, that tag gen with key k1 concatenated with k2, okay, here. So this is your key now, both k1 and k2, and you do the tag generation like this. So in the first part you have tag gen 1 k1 of m. So using the algorithm for tag generation algorithm for pi1 and the key as k1, you run the tag generation algorithm on message m, and you also output tag generation algorithm run on message m using the key k2 following the scheme pi2. So according to both the scheme pi1 and pi2, you generate two different tags of same message m under key k1 and k2 respectively, and provide this as a tag for scheme pi. And then verification works in this manner, that given the message m and two part of the generated tag sigma 1 and sigma 2, and k1 and k2 are known key for the MAC system. So now the verification does this. It verifies whether both tag verify 1 with message m and MAC sigma 1 is a valid message tag pair with respect to key k1, and also tag verification 2 with respect to key k2 implies that m and sigma 2 are valid message tag pair. If both of the conditions satisfies, then only pi is a secure MAC, then only pi actually accepts m sigma 1 sigma 2 as valid message tag pair. Okay, and the second construction is all same except the fact that the tag verification algorithm for the scheme pi will accept m sigma 1 sigma 2 as valid message tag pair if any of the one tag verification algorithm, either tag verify 1 or tag verify 2, verifies m and sigma I to be a valid message tag pair according to sigma pi, according to pi I. So I can be 1 or 2. Now any one of them is secure, it is same. Any one of the MAC scheme pi1 and pi2 are secure. So you would like to answer whether the first one or the second one remains secure. Anyone? Okay, so basically the first one will remain secure, not the next one. The reason being very simple. So let's say that pi1 is not secure, then it is easy to come up with a valid message tag pair for the scheme pi1. So you can easily come up with some m comma sigma dash, right? M comma sigma dash, and let's say this is some sigma double dash. Okay, this is a tag. Now if sigma 1 is not a secure MAC, then this part, that tag verify 1 k1 m sigma dash is 1 with high probability, because m sigma dash can be obtained as a valid message tag pair for the scheme pi1, because pi1 is not a secure MAC. However, to get this test pass, that tag verify 2 with key k2 with m and sigma double dash 1, this is hard to achieve because pi2 is still secure. So because these two conditions are combined with a AND in between them, so even though the first condition passes, the second condition will prevent pi to be to accept m sigma dash sigma double dash as a valid string. So pi remains secure in this case. However, if it would have been combined with a OR between them, then any one of them passes. So if you are able to generate valid message tag pair for either of the MAC scheme pi1 or pi2, then you are able to get the verification of pi passed, even it is not a valid message tag pair. So that is why the first option is an example of secure MAC, but not the second one. Okay, so let us now enter into this week's topics, which are birthday attacks on cryptographic hash function, applications of hash functions, random oracle model, authenticated encryption. So first problem says which of the statements is or are true. Birthday attack on cryptographic hash function requires at least q equal to root 2n number of distinct queries to ensure collision with probability at least q into q minus 1 by 4n. Here n is the size of codomain of the hash function. Anyone would like to answer? This statement is true or false? The first one. So, anyone would like to answer? No? Okay, so what is birthday attack on cryptographic hash function? So in birthday attack, you basically try to find out or maybe try to break the collision resistance of cryptographic hash function, right? So you have to come up with two different input pairs such that h of xi is equal to h of xj, where the query input xi and xj are not equal to each other. Okay, and to find such collision pair, one naive approach is to do n plus 1 number of queries to the hash function oracle, where n is the size of codomain of the hash function, right? Due to pigeonhole principle, with n plus 1 number of distinct input queries, you will get at least one collision in the hash function. However, n is usually in exponential order, that is order of 2 to the power l, where l is the bit size of your fixed hash output length. But it is observed that with 1 true, Shiv Gulam is saying yes, 1 is true. This is exactly the statement of birthday attack condition, that whenever we query with at least root to n number of distinct queries, then the collision occurs with probability at least this q into q minus 1 by 4n, and the proof is discussed in the lecture actually. So the statement is correct, and this is birthday attack because we say that if there are 27 people in a room, then there is at least one collision in their birthday with probability almost equal to 0.5, which is a non-negligible and in fact a huge probability, right? So that is interesting actually. Okay. Next statement says that we should keep the codomain of hash function large enough in order to prevent birthday attack. Is this true? Answer from your side. We should keep the codomain of hash function large enough in order to prevent birthday attack. True or false? This is true actually, right? As I was already mentioning that if you are allowed to query at least n plus 1 number of distinct input query, then by the pigeonhole principle you will certainly find a colliding pair, right? But if you keep your n large enough, that is the codomain size, such that doing n plus 1 number of query means doing exponential number of queries to the hash function, then it is practically difficult to mount this naive attack on the hash function, right? Okay, Shivadulam has answered true. Okay, so this is true, yes. And the last statement is again the same thing, that q equal to n plus 1 number of distinct queries to hash function finds collision with probability 1 due to pigeonhole principle. So all of the three statements are true here, right? Coming to next question. Which of the following statements is or are correct? Merkle tree is full binary tree with hash pointer. Is this true? Anyone? This is true, okay? Merkle tree is full binary tree with hash pointer, because if you remember that what is the construction of Merkle tree? So let's say you have several data nodes. So data nodes are acting as leaf nodes, and you store the hash value of both these nodes, right? Concatenated the hash of this block 1 and the hash of block 2, here hash of block 3 and hash of block 4. You concatenate them, and then you again do the hash of this whole block and store it here, do the hash of this whole block and store it here, and then the final hash value as the root node, okay? So this is indeed a full binary tree, and all these nodes are containing actually hash pointer to their child node, okay? This is true. Tampering with any data node of the Merkle tree is infeasible due to collision resistance of the underlying hash function. Is this true? So, okay, there is answer in the chat. Shiv is saying no. Uh, Tampering with any data node of the market tree is infeasible due to collision resistance of the underlying hash function. Why do you think this statement is wrong? Shiv, you are.
Because it will be to get a data, we will have to make big of k calls, and affecting a node at big of kth position, it will be affecting the next node at its position, big of k plus 1th position.
Correct. So tampering is infeasible, right? So this statement is correct, right? Because of the collision resistance, as you rightly said, that let's say you corrupt this data node. Now this hash value will change because the content of this node has changed, and because this value has changed, the hash of this whole block will change. So this particular content will change, and because this particular content will change, the content of this whole block also changes, and the corresponding hash value here at the root node also changes. So in order to reflect the change at any single node, you have to finally change the hash pointer value at the root node. So if someone has, so usually uh, uh, the person with whom you are actually sharing data of some node has the access to the hash value at the root node, and finally it will match if this value matches with the data node you are giving it to, right? So this value will finally lead to a mismatch if there is tampering with data at leaf node. So it is right to say that tampering with any data node of the Merkle tree is infeasible due to collision resistance, because otherwise you could have managed to uh, tamper the data in such a way that the final hash value is still same, although the data is not same. But only due to collision resistance property, it is not easy to find such tampered data node which will lead to the same hash value in the root node hash pointer. So that is why, so see, your logic was correct. So the statement, I hope you understand that the statement says that it is infeasible to tamper with the data because collision resistance is there for the underlying hash function. Am I clear? So the statement is correct, right? Do you agree with me? How many nodes will a Merkle tree have in order to store 512 unique elements? You mean unique data node. So you can compute like this, right? So you have now 512 data nodes in the as leaf nodes, right? So here you are saying you have total 2 to the power 9 leaf nodes. So you can check from here, right? So at the label just above this, you will get 2 to the power 8 hash pointer node, right? So like that you proceed. So here you will have 2 to the power 7, 2 to the power 6, like that. So let's say here in the, for the case you have 4 leaf node or data node. So here you have 4 data node, here you have pointers, 2 nodes containing hash pointer and 1 node here, right? And the final root node. So like that you can count in this case also, right? Does that answer your question, Kaushik? Okay. Shiv is saying yes. Okay. Kaushik, is it okay? clear. Okay, coming back to the question. The second statement was correct. About the third statement, proof of membership of any data node in Merkle tree needs exponential storage. This is wrong because proof of membership of any data node, so any data node, if you want to prove that this is indeed a member of the Merkle tree, then you should actually give that particular data node, and with that the hash value of that data path. So from the root node to the leaf node, all the nodes present in that particular path, so that will have length in the logarithm of number of leaf nodes, right? So if there is 4 nodes, so the data path has 2 nodes on the way from root to the leaf. So it needs basically you can say that if n is the number of leaf nodes or data nodes, then log n number of storage is required to provide the proof of membership for the data node. So it is not exponential, of course. So this statement is wrong. Okay, that's it. Next, which of the following is or are true for the hash function based commitment scheme? Collision resistance property for the underlying hash function is not necessary for the binding property of the commitment scheme. Next statement says that collision resistant property for the underlying hash function is necessary for the binding property of the commitment scheme. And finally, the binding property can be proved only in the random oracle model. Okay, so anyone would like to answer? Commitment scheme, right? So in commitment scheme you have two phases, you commit and then you open, right? So while committing, so there are two properties essentially which needs to be satisfied by a commitment scheme. One is hiding property and another is binding property. So for any message, right, for any message you have some commitment C computed with the message and say some randomness, right? And binding property says that you should not be able to come up with some m dash r dash, some other message m dash with randomness r dash, such that this committed value is exactly equal to the committed value C, which is commitment of m comma r. If this occurs, then basically the sender can fool the receiver. So there is this sender and receiver. Sender has some message m with it. It computes the corresponding commitment and sends the commitment to receiver r. Next, at some other point of time when the receiver requests for the value inside this commitment to the sender, it can hand over some other randomness value r dash instead of r, so that when it opens the box, then it sees some other message m dash, not the actual message m. So sender is actually fooling the receiver here, but this is not desired in a commitment scheme. So the binding property ensures that this probability that commitment of m dash and r dash is equal to commitment of m comma r, this is upper bounded by some negligible function. Okay, so this is what binding property says. Now in a hash function based commitment scheme, is it necessary that the hash function is collision resistant to ensure the binding property? I think I should wait for your answer for a minute. Okay, so the answer is that it is necessary indeed. Collision resistant property of the underlying hash function is necessary for binding property of the commitment scheme, because uh, the way it is written, you can see here that if we take the hash value of, so if we define the commitment scheme to be like this, right? So having a colliding pair for the so let's say that this so a commitment scheme is defined in this manner, that commitment of M with randomness R is defined as hash of M concatenated with R. Now if we say that commitment scheme does not satisfy the binding property, that will imply that we can have M dash R dash such that their commitment leads to the same value, which in turn implies that H of M concatenated with R is equal to H of M dash concatenated with R dash, which implies that this is a colliding pair for the hash function H, right? But we already know that the hash function is collision resistant. That is why we say that the binding property of the commitment scheme is satisfied. So there is this direct relation with the collision resistance of the underlying hash function and the binding property of the commitment scheme. So that is why we say that collision resistant property of the underlying hash function is necessary for the binding property of the commitment scheme. And what about this random oracle assumption? It is saying that the binding property can be proved only in the random oracle model. This statement is wrong, because you do not need the randomness of hash function output here. It is sufficient to have the collision resistance property of the hash function to get the binding property satisfied for the commitment scheme. It is the case of hiding property where collision resistance of hash function is not sufficient. Rather, you need a stronger assumption where you assume that the hash function behaves as a random oracle model, and then only you can satisfy the hiding property of the commitment scheme. So that is a different case, but for the binding property, the collision resistance property of hash function suffices to make the commitment scheme satisfy the binding property. Okay. So this statement is wrong actually. Okay. This is wrong. Okay, there is some question in the chat. Kaushik is asking, ma'am, can we construct a ROM which is efficient as well as highly secure? So basically, see, random oracle model came to existence because usually we are able to give efficient crypto constructions in the random oracle model. In standard model, usually there is a chance that the crypto primitives that you build from standard model without any random oracle assumption, that are usually practically inefficient. But when we assume the hash function to be modeled as random oracle, we get an efficient scheme. And in terms of security, as you have already seen, that not every instantiation of cryptographic hash function should be used as random oracle, but you can have reasonably good hash function which can be thought of as replacement of random oracle, right? So random oracle model assumption is not like, there is no such truly random oracle available to us, but we are using a hash function and we are assuming that to behave as a random oracle. And for specific instantiation of hash function, if you verify its output to have the desired randomness in it, you can safely use that hash function, and you can get a secure crypto construction as well. Okay, but it depends upon the instantiation of hash function. Not every instantiation of hash function should be used as random oracle. So for efficiency, yes, it is efficient if you construct something with random oracle model, and for security you should choose the correct hash function that you model as random oracle. Okay. Okay, so coming to the next question, which of the following is or are true about random oracle model? Cryptographic primitives built upon hash function are proved secure under random oracle model when collision resistance property of hash function is enough to ensure security of the primitives. So is the statement correct? You can answer this, right? When do we consider the random oracle model? That is when only only collision resistant property of hash function is not enough to prove the security of a crypto primitive. Then only we try to see whether assuming random oracle model will help us, right? So if it is so the statement says that when collision resistant property of hash function is enough to ensure security of the primitives, then of course we will not look further to get the security in random oracle model. We look at random oracle model only when it is not enough to ensure security of the crypto primitives with the collision resistance property of hash function. Though, so first statement is wrong. The next statement says that hash functions are considered to generate random output in random oracle model. So this is true, right? We assume that the hash functions are generating random output, although there can be two such input x1 and x2 where they are related to each other, but still we assume that h of x1 and h of x2 will be independent and uniformly random over the output space. So this is our assumption. Okay, Shiv Gulam is saying true. You were answering the second statement, right? Yes, it is true. It is true. No entity in the crypto system should have knowledge about the internal working of a hash function when modeled as random oracle. What about the third statement? No entity in the crypto system should have knowledge about the internal working of a hash function in random oracle model. Is this true? It is true, right? Shiv Gulam is saying yes. Yes, it is true. Because whenever we say oracle, so oracle service is something that we just query with our input and we just get to see the output. We are unaware of the internal working. In ideal cipher model also we saw that we are assuming that the internal working of the block cipher is not known to anyone. We just query the block cipher and we get to see the output. Similarly, here also when a hash function is modeled as random oracle, so you can just query the oracle with some input x and you can get to see the output of h of x, but how the function h actually works, that is not known to anyone. That is the assumption. Okay. choose the incorrect options. So here there are two properties of random oracle, right? Programmability and extractability. So the first option says that programmability of random oracle allows an attacker to set the answers to the random oracle queries raised by another existing attacker who is being used by the first one in a reduction based proof. Second statement says extractability of random oracle allows an attacker to be aware of the random oracle queries made by another existing attacker who is used by the first attacker in a reduction based proof. Third statement says each entity in a cryptographic primitive is allowed to access the random oracle and they can see each other's query, that is on which input they query the random oracle. So all these are about properties of random oracle that we define. So quickly you can answer writing A, B, C, D, anything about which one are the incorrect. Question says which one is incorrect option. Anyone? Three, she is saying. Yes, you are correct. 3 is the only incorrect one, because as we know that they are just the way properties of random oracle models are defined, programmability and extractability. So programmability says that there is this, say, adversary A and it is using some adversary A dash in the reduction based proof. Then if A dash needs to query the random oracle with some input xi, then what A can do is that it can just assign some uniform random value yi to it and returns yi as if it is coming from the response of random oracle. Okay, so it can just program the output of random oracle. That is the programmability. And extractability is whenever A dash needs to query the random oracle for some input xi, that input is also visible to this adversary A because it is only using A dash as its own service. So all the queries raised to the random oracle by A dash are also visible to A. However, in general, the third statement says that each entity in a cryptographic primitive is allowed to access the random oracle and they can see each other's query. This is wrong, because whenever you say entity in a crypto primitive running, so the random oracle is something present there, and between each of the entity and the random oracle there is a private channel basically. So whatever each of the entity queries to the random oracle, that is hidden from each other. So they do not know each other's query inputs to the random oracle. So here this is different because A is itself using A dash as its own part. That is why A dash's query are visible to A. That is by extractability. But when two different entities are there running some same cryptographic primitive and accessing the same random oracle, then no one should know each other's query to the random oracle. Okay, that's it. Yes, so number 3 is the incorrect option. This is another easy question. Select the incorrect statements. Output of a PRG. So PRG, if you remember from old classes, output of a PRG is pseudo-random on uniformly random seed. Second statement says that seed of the PRG is known to adversary. Then third statement says adversary can query random oracle with any input of its choice. Fourth statement says that the output of random oracle on some query input appears to be independent and uniformly random over the range if query is made by an entity for the first time. You can write the answer in ABCD form, the incorrect statements. She is saying B and D. Let's see. B says seed of the PRG is known to adversary. Of course, this is wrong because seed is something which needs to be remain secret in case of PRG. So yes, this is incorrect. What about D? D says the output of random oracle on some query input appears to be independent and uniformly random over the range if query is made by an entity for the first time. Why do you think that this is incorrect? Sheep. Why is option D incorrect? Okay, so this is correct actually, because how the random oracle functions, you can think of it as a truly random function. So whenever there is this oracle, whenever some entity is querying the oracle with some input xi, you can assume the functionality of random oracle in this manner, that yi is sampled uniformly at random from the output space, okay, and it assigns the value yi as h of xi and returns yi, okay. Otherwise, if xi is always present, so maybe that it just maintains a table of its own for the set of inputs xi and yi. So if some xi is already, let's say I write x and y, okay, so if some xi is already present in its input table, then its corresponding yi is returned, and if some xj was not queried before and is being queried for the first time, then yj is sampled uniformly at random from the output space and it assigns h of xj equal to yj. So it is always the case that for a newly queried input, the oracle just samples a uniform random value, which is independent of the previous outputs, of course. So that value is chosen and returned. So that is why the random oracle output or on some query input appears to be independent and uniformly random over the range. Okay. But if you query with the same xi again and again, you will get the same yi value output again and again. Okay. So this is true. Output of a PRG is pseudo-random on uniformly random seed. Yes, this is true, because only if the seed is chosen uniformly at random from the seed space, then only output of a PRG is pseudo-random. This is true. This is false because seed is secret. Adversary can query random oracle with any input of its choice. This is also true. No restriction is there on the random oracle query, and this is also true. Okay. Which of the following are true for a commitment scheme? Security of commitment scheme relies on the collision resistance property of the underlying hash function. Hiding property of a commitment scheme handles the case when the receiver may be corrupt. Binding property of a commitment scheme handles the case where the sender may be corrupt. A commitment scheme built upon collision resistant hash function is secure assuming random oracle model. So I would wait for your answer and write ABCD. Anyone? Okay. So as I was discussing that there are two property of a commitment scheme that needs to be satisfied. One is hiding property, another is binding property. Binding property I already mentioned that if a sender is corrupt and it first commits with a commitment C corresponding to a message M to the receiver, right? So there is sender and receiver. First it has the message M and it gets the commitment of message M with some randomness R and commits the value C to receiver R. Now when the receiver requests to open the message, there is a request from the receiver end, then sender is supposed to send the randomness information or something such that it can recover the underlying message value. Now if it is the case that with instead of actual randomness used, which is R, it sends some another randomness R dash such that receiver finds the message to be some M dash which is not equal to M. So that means the sender is cheating the receiver R here because there is this probability non-negligible with which that commitment of M comma R and commitment of M dash comma R dash are same. So here the sender is corrupt and this occurrence is not desirable, or it should occur with negligible probability only. So we bind this probability with an upper bound, and this is the binding property of the commitment scheme. And if the receiver is corrupt, then what? So let's say there is two message M0 and M1 and sender sends commitment of any one of them. So I write MB comma R, and now receiver's job is to guess the bit B to guess whether M0's commitment was visible to it or M1's commitment was visible to it. And ideally by seeing the commitment, the receiver should have no information about the underlying message MB. So the commitment should not leak any information about the underlying message MB. That is the hiding property of a commitment scheme. So
excuse me, ma'am.
yes.
So what does this really means? This commitment, is it an encrypted data or something like that, or any
No,
other data?
this is not encryption. So purpose of encryption is just to ensure that privacy is there, right? So it may sound somewhat similar, but it's not exactly encryption scheme. So that is why there is this different name, commitment scheme and encryption scheme. In encryption you have some concept of key, right? So with the valid key owner, so the one who has the decryption key of some ciphertext, it is able to retrieve the underlying message. But here actually later also you can find some examples of scheme where commitment is required to convey the fact, so it can be kind of proof of something. So let's say sender has some data m and it wants to prove to the receiver that I have the valid data m by declaring only the commitment, and the receiver is somehow able to verify that yes, this commitment actually is corresponding to that particular message, although it is not exactly declaring the message itself. Something like that. The purposes are different for the commitment scheme and encryption scheme. In encryption scheme, privacy is the only concern, where for a particular message you get ciphertext, and without the valid decrypting key you know nothing about the underlying message. Here there is also concept of opening the message, right? So if the receiver has the particular randomness or something, then it is able to, only then it is able to open the commitment and see the message. And there can be the case where you don't need to get the opening statement, but yet you can prove to the receiver that I have this message m by showing the corresponding commitment.
Okay, okay.
Okay. Okay. So where are you? So that is about hiding and binding property. So binding property handles this case where basically sender can be corrupt, right? If sender tries to corrupt or sender is corrupt and tries to open to receiver some different message, that is handled by binding property, whereas hiding property handles this case where receiver may be corrupt there. So these two are true statement. And security of a commitment scheme relies on the collision resistance property of underlying hash function. So basically not only the collision resistance property of the hash function, but also the random oracle assumption comes into play when we are talking about hiding property of the commitment scheme. So this is not sufficient. So if we say that commitment scheme security relies on collision resistant property of the hash function, this is not true, because this is not sufficient. Rather, we need to consider the random oracle model to prove the commitment scheme built upon collision resistance hash function secure. So this statement is true, but this is not. Okay, I think there is some funny thing going on here. That is that okay, in the question slide it is written that this is receiver. Okay, so I think this is sender in the question, and now the answer is correct actually. So this statement is wrong. Binding property is handled when sender is corrupt, and hiding property is handled when receiver is corrupt. So that is why these two statements are incorrect here, and in the answer the only correct statement is the fourth one. Okay, now it is okay. Coming to the next question, which of the following is or are correct? Key derivation function can be built upon hash function modeled as random oracle. Okay, so this is true. I think in the lecture only they have clearly elaborated how you can get key derivation function from cryptographic hash function when considered the random oracle model. Okay, this is true. I am not going to detail of that. Hiding property of commitment scheme can be proved by collision resistance of underlying hash function. This is wrong because collision resistance property does not suffice to prove that. Along with that, the ROM random oracle model assumption also has the role to prove hiding property of commitment scheme. Binding property of commitment scheme can be proved only in random oracle model. This is also wrong because binding property of commitment scheme can be proven only with the collision resistance property of the hash function. There no random oracle model is required. So this is also wrong. The only statement is this correct. Choose the correct options from the following. Okay, here comes the authenticated encryption scenario. So it is saying that if an encryption scheme is CCI secure, then it is also authenticated encryption scheme. This is not true. So if you remember that when we say authenticated encryption, what we mean is that two required properties are there for authenticated encryption scheme. One is CCA security. You already know what CCA security is, chosen ciphertext attack security, and there is this ciphertext integrity. So these two are required properties of an authenticated encryption scheme. And if a scheme is already said to be authenticated encryption scheme AE, then of course it will satisfy the CCA security. Okay, so this statement is actually correct. And if a scheme is CCA secure, then you know that CCA is a higher security assumption than CPA security. So a CCA secure scheme is also CPA secure. So we can also say that if an encryption scheme is an authenticated encryption scheme, then it is CPA secure also. So third statement is also correct, but not the other way around, because although a scheme is CCA secure, it can be the case that the ciphertext integrity is not satisfied there. So what is ciphertext integrity? If you remember correctly, that for ciphertext integrity, again we write this game. We write this game that there is this challenger and there is this adversary, and basically adversary can query the challenger with various messages and it can see the corresponding ciphertext. Now the adversary's job is to come up with some other valued ciphertext C star such that decryption of C star is not equal to bot. That means C star is a valid ciphertext, and decryption of C star does not belong to the set of MIs that was queried by the adversary in the query phase. So the adversary should be able to come up with a valid ciphertext of a unseen message. If it is able to do that, then the ciphertext integrity is broken. Then it means that there is the communication going on between two entities, Alice and Bob, and in the middle someone else, some eavesdropper or some malicious entity comes in and sends some other ciphertext which is not really coming from B, but a middleman is sending that message C star, which without the knowledge of the key, of course, because no malicious adversary in between should have knowledge of the key, but still it is able to forge a ciphertext such that that ciphertext decrypts to a valid message which was never seen by the adversary. Okay, for a new message it is able to forge a valid ciphertext. So if an adversary is able to do that, then ciphertext integrity is broken. But for an encryption scheme to be authenticated encryption scheme, this ciphertext integrity property needs to be satisfied. So there can be the case that an encryption key is CCA secure but does not satisfy ciphertext integrity, then it will not be an authenticated encryption scheme. The last statement says if an encryption scheme is CPI secure, then it is also an authenticated encryption scheme. This is also wrong, of course. So second and third statement are correct. Now coming to the next question. There exists a server A who wants. Yes.
One doubt. I have one doubt. CCS security is the must one of the condition for the authenticated encryption scheme.
Correct.
Right?
Correct.
Okay. That must be the one of the one criteria. Vice versa is not correct. If it is CCS secure only, it is not authenticated encryption scheme.
Correct. Correct.
Okay.
So in the hierarchy you can think of this. So there was, if you remember, there was ciphertext only attack, there was known plaintext attack, there was chosen plaintext attack, there is chosen ciphertext attack, and there comes AE, authenticated encryption, which has inside it the CCA security and ciphertext integrity both. So the power of adversary grows in this way, and it is if a scheme is CPA secure, that does not imply it is CCA secure, but a scheme is CCA secure, that will imply that it is CPA secure. In the same manner, if a scheme is CCA secure, then it does not imply that it will be AE secure, but if it is authenticated encryption scheme, then it will be CCA secure. In this manner you can think of it.
Okay, thank you.
So, this question says that there exists a server A who wants to broadcast message to n recipients B1 to Bn in an authentic manner. We are not interested in privacy but in integrity and authenticity, where each user should be assured that the messages it receives are indeed sent by A. For this, the users decide to use a MAC where server A shares a secret MAC key K with B1 to Bn, and each message from the server to the receivers is accompanied by a MAC tag computed with key K. Now, options are saying that using a CMA secure MAC solves the problem, using an SCMA secure MAC solves the problem. Neither a CMA secure MAC nor an SCMA secure MAC can solve the problem, and using an information theoretically secure MAC solves the problem. So I will wait for your answer. So this is a question on the topic of MAC only, nothing to really do with hash function and all. The thing to notice here is that the server and all the recipients B1 to Bn, each of them have the same MAC key K. So anyone? Okay, I think there is. What is the order of changes required to modify a Merkle tree leaf node of depth K? Okay. So yes, Kaushik, I got your question. So what do you think? So what is your answer? I would like to know. You are modifying a leaf node of depth K. Which are the nodes where the hash pointer value will be modified basically if you change one single leaf node? So it's a binary tree, I think it's log n. Yes, you are correct. So n is the number of leaf nodes, I guess, and if you are saying depth K, So I think n is of the order 2 to the power k, and if you are saying that tree has depth k, then I think only order of k number of nodes which are in the path from the root to the particular leaf node that you are changing. So those k number of nodes containing the hash pointer value that will be affected due to the change of that particular leaf node, those needs to be modified. So order of k number of modifications will be needed, right? Does that answer your question, Kaushik? If you are answering in terms of n, then you can write log of n, or if you are answering in terms of depth k, then you can say order of k. Okay. Coming back to this question on Mac, so what is your thought in this? All the parties are actually have the same key k. So do you think that whenever a recipient bi gets some message and its corresponding tag t, Kaushik is saying C. Yes, you are correct actually. That it is neither of CMA secure Mac or CMA secure Mac can solve the problem, because the problem is here the fact that everyone is sharing the same key k. So what can happen is that, let's say what we really want is that the server A, and there is participants B1, B2, B3, Bn. We want that if some message comes from A to some Bi with corresponding tag T, we want to ensure that this tag should be generated by the server only. So if we validate this tag to with this verify algorithm to be 1 with the key k, right, then we know that this is coming from A only. However, since k is known to everyone, what can happen is that, let's say B2 gets this message m comma t from A and just forwards it to B4. Now B4 also validate that m comma t pair with the same tag t and gets the output of verification algorithm as 1 only. Then it will be convinced that it is coming from A, although it is coming from B2, right? This is occurring because everyone has the knowledge of same key k. What ideally could have happened to handle this scenario is that each A comma Bi pair has its own key ki. Then if Bi is getting something that is validated as valid message tag pair using the key ki, then it knows that okay, it is coming from A only. But here any Bi can send a valid message tag pair to any Bj. So the required authenticity that we desire here is not possible. So this is the correct option. Let pi be a symmetric key encryption scheme with message space and ciphertext space M and C, both are L-bit binary string. Then consider a variant pi dash with the same key generation algorithm gen and modified encryption and decryption algorithm denoted with encryption dash and decryption dash with message space and ciphertext space M and C dash equal to 01 to the power L plus 1. So for scheme pi, the message and ciphertext space were L-bit binary string. For the modified scheme, message and ciphertext space are L plus 1 bit binary string. Now encryption k dash m is equal to encryption k m concatenated with a single 0, and decryption occurs in this manner. It just takes first L bits of the ciphertext, it discards the last bit, and then apply the same decryption algorithm of the scheme pi. So this is nothing, okay, just to clearly do this. So encryption is in the modified scheme. You run the original encryption algorithm with message m and key k, and then just put extra 0 to it to get the ciphertext. So this is L bit length, and this one single extra bit that makes the ciphertext of L plus 1 bit length. And when decrypting, so decryption dash, what it does is that it discards the last bit of the ciphertext and run the original decryption algorithm with C0 to CL-1, that is first L bits of the ciphertext, and outputs. Now question is that if pi is multi-message COA secure, then pi dash is also multi-message COA secure. If pi is CPA secure, then pi dash is CPA secure. If pi is CCA secure, pi dash is CCA secure. If pi is AE, authenticated encryption scheme, then pi dash is also authenticated encryption scheme. I'll wait for your answer. What do you think? Note that during decryption, the last bit simply gets discarded. Okay. In the ciphertext, if you notice, the last bit 0 does not really contain any information about the underlying message. All the information about the underlying plain text is contained in the first L bits of the ciphertext only, and the decryption also simply discards the last bit 0 and considers the first L bit of the ciphertext to decrypt. So what about COA, CPA, CCA and authenticated encryption security for the modified scheme pi dash? Anyone? Okay. So basically, if let's say if I say that the scheme pi dash is not multi-message COA secure, then that would imply that by looking at the first L bits of the ciphertext for various messages with the same key k, I am able to learn something about the underlying message m, correct? Now because the last bit 0 does not really contain any information about the plain text, it all boils down to the first L bit of the ciphertext, which would in turn imply that I should be able to gain information about the underlying plain text by looking at the first L bits of the ciphertext, which is nothing but the ciphertext corresponding to the original scheme pi. But pi is already known to be multi-message COA secure. That is why pi dash will also be multi-message COA secure. So first statement is actually correct. And similar argument goes with CPA security as well, because if pi dash is not CPA secure, that will imply that by exploiting the encryption oracle, it is possible for an probabilistic polynomial time adversary to distinguish between the ciphertext of two different plain text m0 and m1. And as you can see that in the query phase to the encryption oracle, the amount of information learned by an adversary in the game for pi dash is exactly equivalent to the game in pi. So if it is possible to differentiate with non-negligible probability between encryption of m0 and m1 in case of the modified game pi dash, then it is of course possible to distinguish in the game of pi as well. But pi is already known to be CPA secure, then pi dash has to be CPA secure as well. So this is also true. However, this argument does not go along with the CCA security case, because here you can actually exploit the decryption oracle to get to know about the underlying plain text. So once you see the challenge ciphertext, so let's say what happens in the game. So adversary has sent two messages of its choice to the challenger, and the challenger has sent encryption dash k of mb, which is nothing but encryption of mb under key k concatenated with 0. So this is the challenge ciphertext. Now the adversary can actually query the decryption oracle with this. So the first L bits are same, okay, but the last bit it can flip it to 1. So this is not same as challenge ciphertext. So this is a allowed decryption query to the decryption oracle, and in response it can see the value of MB, because the decryption just discards the last bit and applies the normal decryption algorithm of scheme pi to decrypt it, and as a result MB is visible. So because M0 and M1 are already known to the adversary, it with probability 1 it succeeds to get the bit B in this CCA security game of pi dash. So although pi is CCA secure, pi dash may not be pi dash is not at all CCA secure the way pi dash is defined here. Okay, you can easily exploit the decryption oracle to know about the which underlying plain text among M0 and M1 are encrypted as the challenge ciphertext. So this is wrong, and since it is not CCA secure, it will not be authenticated encryption scheme as well. Just analogous to the way we say that if a scheme is not CPA secure, then it definitely will not be CCA secure. Similarly, if a scheme is not CCA secure, it will definitely not be authenticated encryption scheme. Okay, so the last two statements are incorrect here. Next question, let M0 M1 be the plain text chosen by adversary in the challenge phase. Challenger encrypts any one of them, say MB, as CB equal to this is the answer. Okay, so next question is this, let pi equal to j in encryption decryption be a symmetric key encryption scheme with message space M. We construct a new symmetric key encryption scheme pi dash with gen dash, encryption dash and decryption dash for message space M dash as follows. Key generation algorithm gen dash outputs k equal to k0 k1 as its key, where gen dash invokes two independent instances of j, which outputs k0 and k1. Okay, to encrypt a message of the form M0, M1, the encryption algorithm outputs C0, C1, where C0 and C1 are respectively the encryption of M0 under key K0 and encryption of M1 under key K1. The decryption also works in the similar manner. Now comment about the again multi-message UA security, CPA security, CCA security and authenticated encryption. You can think in the very similar manner as the first one, the previous question.
Ma'am,
Yes.
in the previous problem, if pi dash is not CCA secure, then it is also not a authenticated encryption scheme. That is right, now, ma'am?
Right.
Okay, thank you.
So you can answer this question also in the similar manner. Note that in the key generation function, both the key k0 and k1 are chosen uniformly at random. So the two encryption instance here in the modified encryption algorithm. So encryption dash works in this manner, right? So you have two key k0 and k1 available, and you have two messages, right? m0 and m1, and you are doing this. So if from this you are able to get any extra information about the underlying message m0 and m1, that would imply that the basic encryption scheme pi is also not satisfying the multi-message CUA security or CPA security also. So for both the first two cases, due to the multi-message CUA security of the underlying scheme pi or CPA security of the underlying scheme pi, you can argue the multi-message CUA security and CPA security of the scheme pi dash as well. But for the CCA security case, you can actually make use of the decryption oracle. So maybe what can you do is that you can choose your message in the challenge phase in this manner. Let's say this is m0 comma m0, your first m, and the second message is m0 comma m1. So they are the two messages, and your challenge ciphertext is encryption of any one of them. So it has the form encryption of k0 m0 comma encryption of k1 mb. This is your challenge ciphertext. Now if you are able to determine what is the underlying message of this part, then you are done. So what you can do is that the adversary can query. So let me denote this part as CB1 and this part as CB2. So in the decryption oracle query, it queries with some other ciphertext CB dash, where the first part can be any valid ciphertext, okay, apart from CB1 itself. Okay, so let us denote CB double dash. It will be some valid ciphertext, okay, that you can gather from any encryption of the query phase. It can be anything but not CB1 exactly, but the second part CB2 remains exactly the same. And now when it gets decrypted by the challenger, this will lead to some arbitrary message m, but this CB2 part will exactly return either m0 or m1. And looking at that, you can say whether the challenge ciphertext CB is encrypting this m0 or this m1, right? So that is how you can differentiate between the two cases by exploiting the decryption oracle. So CCA security is not there, and since CCA security is not there, pi dash will not be authenticated encryption scheme also. Okay. And the last question here, let encryption comma decryption be a AE secure cipher. Now there are two modified scheme here. The first one does this encryption dash equal to encryption k of m comma encryption k of m, and decryption checks whether decryption C1 with respect to key k is exactly equal to decryption C2 with respect to key k. then only it returns decryption of C1 with respect to key K, otherwise it rejects. And the second one, first you do the encryption of M under key K and get the ciphertext C, and then duplicate the ciphertext C twice as C, C as the ciphertext, and during decryption it checks both the halves of the ciphertext C1 and C2. If they are equal, then only it tries to decrypt, otherwise it rejects. Now we have to show the first scheme is not AE secure, but the second scheme is AE secure. So basically you can see that you can break the CCA security of the first scheme. How? So just analogous to the previous example, you can actually query with let's say for the first scheme, the adversary can query the challenger with two message M0 M1, and in return it sees C1 C2, where C1 is some encryption of MB, C2 is also some encryption of MB. They may not be same because encryption algorithm is randomized. So I am writing C1 C2 instead of writing C1 C1. Now it can again to the decryption oracle, basically let's say it first queries the encryption oracle for some valid encryption of M0, and it gets to see C0, which is some valid encryption of M0. Now query the decryption oracle with C0 comma this C2, right? The next part. Now there can be two cases. One case is that if if C0 C0 is indeed an encryption of M0, right? Now in the decryption oracle, it checks that decryption of C0 is equal to decryption of C2 or not. So it can be the case that C2 is an encryption of M0, right? If that is the case, then decryption of C0 with respect to key K and decryption of C2 with respect to key K, they both will match because both of them will return M0, and then M0 will be returned by the challenger as a response to decryption oracle query, and with probability 1 the adversary wins. And another case could be C2 is an encryption of M1, then decryption of C0 with respect to key K, which is M0, will not match with decryption of C2 with respect to key K, which is M1, and in that case decryption oracle will reject, right? So there is clear difference between the two cases which can be exploited by the adversary to win the CCA security game with probability 1. So the first game is necessarily not CCA secure, hence it will not be AE secure as well. What about the second scheme? Here actually the same kind of attack cannot work, because whenever you see the challenge ciphertext of this form C, C, you cannot necessarily change it so that some C comma C dash is there and you get to see the decryption of any one part. You cannot do that because it checks the equality of these two parts of the ciphertext. So this kind of attack will not work in the second case. So you can see that the second scheme is indeed CCA secure, and you can also check for the ciphertext integrity, because again if you have to come up with a forged ciphertext for a forged valid ciphertext for some unseen message, then you have to generate such C star comma C star such that it is an encryption of M star not seen in the query phase, which is again difficult due to the underlying scheme AE secure, encryption comma decryption, because this is AE secure. This encryption double dash decryption double dash will also satisfy the AE security. Okay, so this is it for this week. If anyone has any doubt of these questions, you can let me know, otherwise I can end this session. Okay, so I think okay, so I am concluding this session. Thank you for attending.